All right, why don't we go ahead and get started? Hopefully everybody is here for functional programming techniques in C#. We're going to talk through what's available, what's there, and what we can do with it. First thing is I want to thank all of our sponsors for this conference. I know this is a unique situation in a unique year, and it's really important that these companies are putting effort and resources behind enabling a conference like this so that we can all learn and grow and continue practicing our craft. So if you have the opportunity, please go see these folks, talk to these folks. They really, really would like to talk to you. All right, so who am I? My name is Darren Hale. I'm a software creator. I've been doing software development for over 20 years at this point. I'm really easy to find online. I've got all my contact information there. I've also got it at the end of the slide or at the end of the presentation, so you can get a picture of it at that point as well. All right, so the challenge, or a little bit more about me and what we're going to be doing here. So I am the kind of developer who is always looking to try to improve myself. I'm always looking for better ways to do things, new ways to do things, and trying to improve myself as I go. One way that I do that is I'm a test-driven development person. I always write tests before I write code. When I say that, I always write tests before I write production code. If I'm learning something new or I'm just experimenting with something, I may not always have a unit test there, but more often than not, I find that I will write those unit tests when I'm exploring and learning, because it's the opportunity to exercise the thing that I'm creating and exploring and learning. So test-driven development is really, really baked into me. One of the things that I've grown to learn over time is that I want to keep my tests very straightforward. Very early on in my career, I would joke with people that if you gave me a debugger and a code base, I could figure out what it did and tell you what it was doing. Nowadays, I say if you give me unit tests in a code base, I will figure out what it is and what it is doing. If I have to get into a debugger, it starts to indicate that that code base may be a little more convoluted and a little less easy to understand than I would like it to be. So I really push to have my tests be straightforward, even to the point of them being longer and more verbose. If they are communicating what a particular bit of code is doing, I would prefer to have that up and going. I'm also a big believer in that the code should reflect the complexity of the problem. If I'm dealing with a very complex problem, the code will be as complex as the problem. What I don't want to see is complex code for very simple problems. And it's very easy to do in an object-oriented world to create layers of abstraction, especially if I'm trying to do good test-driven development and separate things out really nicely, that I may create more abstraction than I need for the problem at hand. So I'm trying to keep things simple and easy to understand, usually for that next developer coming up, which is generally me in an hour, 2 hours, or a week later when I'm going back to look at my code. The other thing that's really, really important to keep in mind in all of this journey with functional programming is that I am an object-oriented developer at heart. When I was introduced to object-oriented development, it resonated with me. It's one of those where, like, if you're looking at one of those 3D pictures, the picture jumped out at me immediately. I got it. I could see the objects. I could understand that abstraction. I maybe didn't always understand the finer details of it or the finer points of object-oriented development from an early stage, but it resonated with me. Being able to model the world, the software world in concrete objects just made sense to me. It made it easy for me to communicate with people. It made it easy for me to understand. So deep down inside, I'm an object-oriented guy. I see the objects, I see types pop out in my brain. It's important to know as we kind of go through this talk that that's a deep-seated piece of my being that as I'm trying to move into functional programming, it's a little hard to get around. Okay, so where did I get introduced into functional programming? There's a tech conference here in St. Louis called Strange Loop. And Strange Loop is, I want to say an alternate languages conference, but it's really not at this point. It started out of a meetup called Lambda Lounge, probably 15, 20 years ago. And that meetup focused on, it was people getting together talking about their experiences with functional programming languages, which at the time were not very mainstream. They were a little bit strange. The conference Strange Loop was basically focused on more of these alternate programming techniques that were being used to scale companies like Twitter and Netflix. But they had a very, very hard bend on the functional programming languages. I think it was around 2010 or 2012. I forget exactly which year. I think it's probably 2010. I was sitting in one of the talks by Jim Wyrick, the one that I have linked here on the slide. He was sitting at the podium, live coding in Emacs, the factorial problem using Clojure. And Clojure is a Lisp variant, a lot like eLisp and Emacs or Common Lisp, if you're familiar with that. And he was walking through the combinatorial problem, and he created it in Clojure with a function, and then he started to refactor it. And the purpose of his talk was to go through lambda calculus, which is one of the fundamental math theories behind functional programming. But as he did that, I was witnessing him extract pieces of code out that I would never have thought in my object-oriented way of thinking to extract out. I sat there realizing that I had seen something very, very powerful, but I could understand none of it. I had gone back and watched that video a couple times shortly after that conference. I tried to mimic what he did, but I could not get it to resonate exactly with me. But it did point to something that I wanted to learn. I could recognize that there's a higher level way of doing things, and I wanted to understand it. But being an object-oriented developer, this was not a part of my daily life. So it's taken me a very long time to kind of nip away at this thinking and to get to where I am right now. All right, so let's talk about functional programming and what it is. I'm going to start with object-oriented programming because I assume most people here are object-oriented programmers and they understand that. In an object-oriented programming language like C# or Java, the central construct is a class. Everything that we do in these languages is based around creating a class to define an object. A class could have data, it can have methods, it may or may not have one or the other depending on what you're trying to do with it, but everything is based around a class. Alternately, in a functional programming language, the central construct is a function, or more precisely, an expression. An expression yields a result. In C#, those are always functions or methods, generally speaking. They could also be assignments, but they're generally functions or methods. But their construct is that expression. They can pass them around. They can work with them. They're first-class citizens. C# is fundamentally an object-oriented programming language. Its central construct is a class. But in recent versions of C#, they've introduced the constructs necessary to make functions first-class citizens, giving it the capability of working more like a functional programming language. So let's talk a little bit about functional programs. And here we're going to talk through some of the ideals of a functional program. A lot of these ideals could equally apply to object-oriented programming languages, but they are definitely tenets of functional programming. They are in some cases baked into the language constructs of some functional programming languages. So I think understanding these concepts will help us better understand what C# has in there and how we can then leverage that in good ways moving forward. So the first characteristic of a functional programming language is purity. What this means is that any function given the exact same two inputs will always yield the exact same output. The easiest way to think about this is to think of math. If I have two integers going into a function and it returns an integer coming out every single time, that's a fairly pure function. Pure functions are easy to test, right? In the case of math, they're very deterministic. There are no extra cases, there are no weird cases, there are no extra things that you need to worry about. So purity is a really key tenet of functional programs. A couple of examples of pure functions. So the very first one, the sample one, it's a function that returns an int, and it simply returns 42, the universal answer to everything. That one is absolutely pure because given no inputs, it will return the exact same output every single time. The next one, sample 2, is the math one that I was describing. Given two integers in, it will return an int out that is the result of the first two being added together. This one is really pure too. The third one, by the definition of purity that we're using for this talk, is still pure. Given two ints, it returns the sum of those ints, but it's also doing a write out to the console. There's a little bit of impurity there, right? I can still test it really well. I can guarantee the inputs and the outputs. So from our definition, it's pure, but it's starting to inch down the path of being a little less pure than we would like. To understand purity within code, I think it's also good to look at what is impure code. So in this case, getting the current seconds, that method returns datetime.now.seconds. It looks a lot like our very first sample that was absolutely pure in that it takes no inputs and returns an int output. But for every call, it is going to return a different int every single time. So that one is absolutely impure. The one below it is also impure. Given a string coming in, it's going to give you a string coming out. It looks like it should be a pure function, but because it's embedding the datetime.now, the string coming out is going to be different every single time. Both of these functions, even though they are fairly simple, are really, really hard to test because their output is non-deterministic. So these are impure code samples. A few more examples to look at as well, just to make sure we really get a handle on it. On the left, we've got a function called getSum that returns an object called sum, and it takes in 2 ints. It implements some business logic that says if the ints coming in are negative, return null, otherwise return a new opt object with the result of the sum. On the surface, it looks like it should be a pure function. It takes in 2 ints, it returns the sum out. But because that sum could be null, which is not actually a type, or the type of sum, it is not as deterministic as we would like it to be. Therefore, it is an impure function. We see this kind of code quite a lot in C# programming. On the right, we see getSum number 2. It looks a lot like our other examples. It takes 2 ints in, it returns an int out. But instead of using null to return something out, we've decided that if the input are negative, we're going to throw a new exception. This one is wildly impure because it's not only not necessarily giving me an int coming out through every single code path, but it will actually change the flow of the program overall and is really, really hard to test. So these are some of the common programming constructs we see in C# that are not pure from a functional programming standpoint. The next characteristic of functional programs are that they are easy to reason about. Generally, functions are grouped together to work on similar items. This easier to reason about concept and grouping functions around similar items allows for a very fluent code style. It allows code to read like prose, almost like a kindergartner giving you a set of directions for making a sandwich, right? First I get the bread, and then I get the peanut butter, and then I get the jelly, and then I put the peanut butter on the bread, and then the jelly, and I smash them together, and then I'm done, right? It's a very easy way to understand it. It's a very rudimentary way to understand things, but it communicates meaning very, very well. An easy example of this is ASP.NET Core applications. When you're configuring an iApplication builder, like in this code sample, it is in a fluent syntax and it's very easy to read. And you can picture that kindergartner reading this over to you to explain what it's doing. I'm going to have the app use HTTPS redirection. I'm going to have it use authentication. It's going to use CORS, and then it's going to use MVC, and then I'm all done. So functional programs are generally easy to reason about. Another characteristic of functional programs is immutability. The definition of immutability is that things don't change. So when you're working to create stateless objects in object-oriented code or a stateless system, you're making it immutable. You're not changing things as you go through. Once something is created, it is that way forever. Some examples of immutability. So this first one with the addition method, it takes in a math problem and returns a math problem. It sets the answer property on the math problem that comes in and returns that going out. So this is actually mutating state, right? This is not an example of immutability. This is the exact opposite. The right way to handle this from an immutable standpoint is that I create my result from the object that comes in, and I generate a new object that I return out. So that the original object stays the same, I get a brand new object that's got the new result. Everything is immutable and stateless at that point. Hopefully everybody's keeping up. If I'm going too fast or these are getting out of hand, please pop something into the chat and I can maybe go back and readdress things. The next characteristic of a functional program is consistent behavior. When you call a function, because it's pure, because it's immutable, it's going to do the same thing every time you call it. So it allows you to codify what we consider in C# some boilerplate code. It can help create consistent behavior around things like logging, exception handling, and stuff like that. This one's going to be a lot easier to understand once we get a little further into this talk. So the code that points this stuff out is going to come up later in the talk. Another characteristic here is sophisticated reuse. It kind of goes along with the consistent behavior, but by using functions and treating functions as first-class citizens, we're able to create some higher order abstractions, and we can use function composition, a lot like we use object composition, to create some truly powerful mechanisms that allow us to really codify certain behavior and standardize certain behavior across an application or even an enterprise. Okay, C# and functional programming. What has allowed this is that C# has added the constructs to make functions first-class citizens. And what that means is that you can define functions as data, you can pass functions as data, functions can be passed as parameters because they can be passed as data. They can also be return types from functions. So they are first-class things, just like a class in C#. You can return an object of a class type as parameters, as variables, as return types. Functions can all do the same thing as well. So just some examples out of some C# code that's dealing with this, and a lot of this will look familiar to C# developers, right? The first line, I declare a delegate called math calculator. It defines a delegate that takes in an int and returns a decimal. This is creating a function type, right? It is a declared type that we can use with the compiler. The next function down, that square function, would actually fulfill the delegate type that we declared as math calculator. We can see in the calc circle area call that it is taking a function as a parameter using the func type, and we'll get into the syntax of this in a little bit, along with a radius. And then it does its calculation by calling the function that's passed in with the other value that's passed in times pi, because I needed to get it fit on a slide, and returns that value back out. And then lastly, the last version of calc circle area actually declares a function and returns that function out, and it's using the lambda syntax to return a function out. And if some of this stuff looks unfamiliar, we're going to get into these constructs in much more detail coming up. All right, so these are the constructs that we really looked at and that exist within C#. We have delegates, actions, functions, lambdas, and extension methods. I call out extension methods because they technically employ some functional programming techniques to work, but I don't get into them because they don't work really well with our principles of a functional programming language that we talked earlier. They're also a special beast within C#. They're useful, they're fantastic, and they probably deserve a talk all unto themselves, but I'm going to focus on the top 4 as we go through in this talk. All right, so first up are delegates. A delegate is a type. It declares a type within the type system within C#, and it represents a reference to a method. So much like we had in the example before, I declare a delegate called add2 function. It takes an int and returns an int. I can then declare a variable adder of type 2 function and assign it to a method called add2. Okay, functions. Functions are exactly what they are. They are a typed function with generic types, either passed in or returned. And a function is a delegate that has 0 or more input parameters and a defined output. And it follows this type thing of func t, comma t result. And what that means is that the last type in that expression, in the angle brackets expression, represents the return type of the declared function. All of the types declared before it represent the input types. So below, I've got my add2 function declared as a func, and it takes in an int, and it returns a long, and then one that would satisfy that type down below is add2. It takes an int, it returns a long, and I could assign add2 to the add2 function. Action. Action actually goes along with the function type, and it is a delegate with no return value. It can have up to 16 input parameters. So it's a lot like the func keyword type, except there's no return type. So instead of having an empty angle bracket, they created the action type. So in this case, I can declare a function called print message of type action that will return string and take no, and it will be a void type, but it will take a type string. So message printer declared down below takes a string as an input parameter has a void out parameter or void return type and just does a console log or logging to the console. Print message is declared here. It could be assigned as message printer. It could also be assigned as console.writeLine. So you can start to see some of the power and flexibility that the functional programming techniques will give us as we move forward. Lambdas. Lambdas are fun. So a lambda expression is an expression that has an expression as its body or a statement block as its body. And I hate definitions like this. It's an absolutely terrible definition. But essentially what a lambda is that it is an unnamed, somewhat dynamic type of either a single statement or an entire block of statements. So it can be an entire functional unit. We see lambdas quite often using link in C#. So in this case, I've got an int array. I want to create an array of the doubled versions of that. So I can call the array.select, which is my link call, and then pass it the lambda expression that is a function that will take a single argument, x, and it will take x and return it doubled. Another place that we see this is in ASP.NET Core MVC. When you are configuring different properties within that subsystem, quite often that's done with a lambda expression. So in adding API versioning, there's a property that gets passed in. That property then, that P property has properties of its own that you can set and configure within that block. A few other versions of lambdas, and I want to get into these because they get kind of interesting and really started to help unlock what C# can do for me as well. So let's go back to our calc circle area. It has a parameter of type func coming in, and it's going to use it to calculate the area of a circle. I can declare my square function as a func that takes an int and returns a long, and declare it as a lambda expression that has one input variable of x and returns x times x. That's that middle line in there. When I first saw this syntax, I didn't think that was actually valid C#, and I had to go try it out. It is valid C#. So you can declare entire functions in a single line like that if you need to. I can then call calc circle area with that square function that I just declared. I could also do that with an anonymous delegate or an anonymous lambda expression like I have above the line break, where I'm declaring a lambda that takes in a single integer or a single parameter x and returns x times x cast as a long. That works as well. So if I have calc circle area and I need to change the way I'm doing that r² calculation, I could potentially change that on the fly. Another way to see that as well is the record message example that I have down below. This one's declared to take a generator that is a function that returns a type string, and it takes in a string message. It calls the generator plus the message. And when I call record message, I can send in a lambda expression. The open parens means there's no input parameter, and it's going to return parse string dot the substring and take the pieces out. And then my record message is going to concatenate the two pieces together. So lambdas give us a lot of flexibility to kind of do things on the fly, do things as we need them in place without necessarily declaring a formal function and compiling it. The trade-off with lambdas is that they are not compiled, and there are some advantages to declaring things as either delegates, actions, or functions and being able to use them as a compiled type. Some more examples that I throw up here just to make sure that we're really kind of sinking into what C# can do with all of this stuff. Right here, we've got a triple function. It takes an int, it returns a long. I declare a delegate called multiplier that defines a type of function that takes an int and returns a long. I can then declare a variable called tripler of type multiplier and assign it that triple function. I then declare a print math function, and it takes as its types a func that takes an int parameter and returns a long called calculator, and then an integer of a supplied value. I declare another function called print math typed. He takes a multiplier type function and a supplied value. They both call calculator on the supplied value. They log the result out with a message on the console using console write line. Down below, though, in the little main snippet that I have at the bottom, I can call print math with the triple function that I declared above because the types match. I can call print math with a lambda expression like I have where it's really quadrupling the value instead of tripling it. But math typed can only be called with that tripler variable because it requires a parameter of multiplier. So the type that it's expecting is of type multiplier. If I try to pass it a lambda or a func definition, it will fail at compile time. So if I start doing a lot of work with functions and I want some of the type safety that C# provides, I can use delegates, funcs, and actions appropriately to declare types that allow me some compile time checks within my code. That gets to be a very powerful tool in our tool belt when we're going through some of this stuff. Okay, so before we move on, is everybody following along? Are we keeping pace a little bit? I haven't seen any questions pop up, so I assume we're doing okay there. Good. So the question popped up about why are all the examples static? Yeah, there is a reason, actually. So in a lot of functional programming languages, when you declare the functions, they are essentially static. That's how they achieve some of their immutability constraints. If you really get into doing functional programming in C#, the safe way to do that to help keep you from creating mutable things is to declare them as static. It forces you to think about the immutability aspect. So since I want to get people thinking about functional programming paradigms, I'm declaring most of my methods as static in these examples. That's a really good question. Very good question, actually. All right, so why would we want to use any of this stuff in object-oriented programs? We talked earlier about reusing algorithms. I want to get into what does that mean and where can we use that. We talked about higher order abstractions, and that's really a way that we can reuse some of our algorithms. There are some performance improvements, and we were just talking about that a little bit, in that you can have compiled function types and compiled functions that can be passed around. There's an inherent performance improvement when you use the compiler to build some of that stuff instead of dynamically throwing that like lambdas and anonymous lambdas on the heap as you go. But having those things pre-compiled gives you a performance boost. And then generally speaking, I have found that it simplifies testing. If I'm using a functional technique or static methods, in order for the static method to work right, it can't mutate state. It makes testing a lot easier. Those become fairly basic things to test and to reason about and understand. So those are some of the big reasons why I like to use functional techniques in an object-oriented program. We'll also, as we get to the end, we'll start talking about where this is cropping up and why, as we understand this better, some of the packages and other areas where we're seeing this and why this is becoming more prevalent. So the first real-world application, and I want to set this one up a little bit. I attended Microsoft Build a couple of years ago and attended a talk by Kathleen Ballard where she was introducing some of the latest functional techniques in, I believe it was C#8 at the time. And she walked through this example and it really started to resonate with me. In object-oriented programming, we are very, very comfortable with the concept of refactoring. In fact, it's just baked into our being. It's baked into Visual Studio at this point, right? There are tooling commands you can call to just grab a snippet of code and refactor that out. And generally what we're doing is we're taking a chunk of code, like on the left, the part that's highlighted in orange, we're pulling it out into its own method, like the bottom right, and then we're calling that method in the original code, like the top right, right? That's an easy paradigm for us to understand. We've got, say, an if-else block, and both pieces, the if logic and the else logic, are fairly large. One way to simplify that down and make that a little bit easier is to pull the logic out of each block into their own methods, test those methods individually, and just call those methods from within the if. So that shrinks our code way down, makes it a little easier to read. This is generally considered inside-out refactoring. I'm taking the inside bits and I'm popping it to the outside to do my refactoring. If you were using functional programming techniques, one way that you could start thinking about this, well, let me back up. Let's go through the example first, the inside out, to make sure we're keeping everybody with us. So on the left, I've declared a calc payment method. It's taking in an amount and a term for a loan, let's say. It's setting a default payment of 0. If the length doesn't equal 0, and I'm doing a good safety check because I'm a good developer to make sure I don't do divide by 0. If it doesn't equal 0, I do my division, casting it as a decimal and to create my raw payment. I then figure out an interest rate, and I hard-coded the interest rate here just so we could see the logic, and then I return the payment back out. If I needed to refactor that, I would grab that part in the orange block. I'd pull that out like I did on the bottom right into a determined payment. It takes the same amount and the same length. It's going to determine the raw payment, do the interest rate, and return it back out. The if check then up above stays the same in the calc payment refactored. I call my method below, and I've refactored this out. I can now test determine payment separate from calc payment refactored. Everything's good. This is our normal object-oriented way of doing things. In a functional approach, we have an option of doing what Kathleen Dollard termed outside-in refactoring. And in that case, we generally take the block, the outside portion from the last example, and pull it into its own function like I'm doing here. So on the left side, the block that I'm going to pull out is in orange. I pull it into its own function down on the bottom right. And the logic in blue that had always existed, I'm going to pass as a function or a delegate into the extracted algorithm, if you will, and call it from there. This is much, much easier to see in a real world example. So let's go back to our payment here, right? If I'm calculating a payment, I'm most likely working in a financial services application or enterprise. That check for 0 to make sure I'm not dividing by 0 is going to be prevalent in a lot of different places. So I can take that if value does not equal 0 check and pull that up into my is0 method in the top right. All I'm going to do is return either true or false. If the value is 0, it is 0 true. If it isn't, it's false. I can then refactor my calc payment method like the bottom right, where the raw payment gets calculated with a ternary expression. I'm going back to that expression syntax. So a lot of people will argue, why is this not just like an if-else? Part of the reason is that in a ternary expression, it results in a value coming out. So is 0, that if check on the length, is going to either return 0 in a decimal if the length value is 0, or it's going to do my logic for the calculated payment. I don't have a choice about not assigning that value. Whereas when I write an if block in traditional C#, I as the developer have to pay special attention to doing all of the assignments right. If I don't get them right, I end up introducing a bug into my code. In this case, I can use the compiler and the ternary expression to ensure that raw payment is assigned a value of the right type every single time. So in this case, I'm able to extract that outside portion, the algorithm portion for the 0 check. I can reuse it all over the place and start replacing what could be complicated if blocks with these ternary expressions where I'm guaranteed the right assignment everywhere. Now, if there's logic around if the raw payment is 0, don't calculate an interest rate or create a default payment because the interest rate hasn't kicked in. If there's other logic like that, I have now eliminated the need to do a lot of the safety checking that has been going on in a lot of C# code. Yep. So Jacob wrote about, understanding the static thing, that static methods become, or the classes of static, but these static methods become modules of methods. And that is exactly right. Right, since you don't have fields, your objects in those cases generally become data passing. And I'll talk through a little bit more of this as we come up, especially with some of the things that are going into C#9. But yes, you're right on target with that observation. How are we doing with the outside-in refactoring? If it's still a little fuzzy, it's okay, because I've got a few more real-world examples to really start to hammer this in and to think through this. So the one that really made this click for me was seeing try, catch, get refactored. And I didn't do it complete justice right here, but we'll talk through this a little bit. So on the left, I've got what I consider to be fairly good C# code in that I'm doing some division by 0, I'm wrapping that in a try catch because I know I could get a divide by zero problem, even if I'm doing my if checks somewhere else. I catch that exception, I create a message, I create my return thing coming out. This is pretty safe, right? This is pretty good. And we see this kind of stuff everywhere, right? One way to think about reusing this is for exception handling, because I know in my experience, if I do exception handling on 2 different days, or I do exception handling in the morning and then I do it somewhere else in the afternoon, it's going to look slightly different. I'm generally not consistent with my exception handling. But what if there's a way to make exception handling absolutely consistent and to make it a very simple tool for developers to use? And that's where you could refactor from the outside the try-catch block and pull that into a function that takes a workload function. So that's what I've done on the right side. I create my try-catch method that takes a function that's going to return a decimal called workload. The try-catch is going to return a type of iResult. So I'm going to lean on my typing system a little bit, but that's okay in these realms, right? There are a lot of functional programming languages that are strongly typed. I'm going to call my try-catch. In my try, I'm going to declare a new result object of success result. So it's an inherited type of my interface. It's going to set my value, which is the result of workload. It's going to set a success message, and then it's going to return that result coming out. If an exception occurs when I call workload, I'm going to fall into my catch. In there, I'm going to declare a result object of failed result. I'm going to set the result value, I'm going to set the message, and I'm going to return the result. So I'm doing all the same things in both spots. The difference being is that I can test this with unit tests up and down. It is absolutely deterministic. I don't have to worry about throwing exceptions, catching exceptions, and the weirdness that goes along with unit testing those things. I can also reuse this try-catch everywhere. And I used a fairly simplistic example at the bottom where I call try-catch on a lambda that takes nothing in and returns 1 divided by some value just to prove that this works. If you start to take this approach where I'm extracting the boilerplate, right? A lot of this try-catch stuff we generally call boilerplate within a lot of the C# programs. I, as an architect or as a team lead, can extract this out into a library of try-catches that take function workloads in and return my common iResult out. That is well-tested, well-tried logic. Now when a developer needs to wrap something in exception handling, they can do like we did below and just put that into a function, name the function, pass the named function into try-catch. Or they could declare that entire function as a lambda expression where they're at. And the other really big advantage here is that if I've already got existing code that isn't wrapped in try-catch, instead of going through and dirtying up those functions with the try-catch syntax and reformatting and worrying about all of that stuff, I can just call that named function within my try-catch at this point. So it starts to really open up what I, as an architect or senior dev, can do to enable my team to move faster, do things more consistently, do things a little bit faster as well, because now my try-catch is a compiled element and not being done on the fly as I load every single object or method, and it can be consistent. I know I get a little bit worked up about that, but that to me was really where this higher order abstraction concept really started to come together. Go back for a second. Where the idea of the outside-in refactoring really came together, and where the concept of the functional composition really starts to come together as well. I create a function called try-catch. It takes a function that is my workload. So I'm using multiple functions together to get a result back out. This higher order approach will enable, say, more junior devs that if they want to wrap something in try-catch, they don't need to think about the mechanics of it. How do I log the message? How much of it do I log? Do I put it to the console? Do I use a logger? All of that stuff is solved for them and consistently for everyone on the team. All of a sudden, these techniques are becoming, it's starting to light up. It's like that 3D image jumping out of the picture. I can see that image jumping at me on ways to use these techniques to really enable development teams to move faster and to do more around business logic and less around algorithms and boilerplate. Okay, so now that we get all worked up and I'm super excited about this stuff. We're going to get into function composition. And this is probably where I get myself twisted up and confused a lot faster than any other area in functional programming. It's still where I'm really learning on the right approach and the right way to do this stuff. Let's take, for instance, this multiplier with timing, right? Quite often we will have not as simplistic of examples like this, where we want to put timing calls into our code to understand how fast something's running, especially when we're doing performance tuning and things like that. So in this case, I take in two ints, I return along, I'm returning the result of those two ints being multiplied together. At the start of the operation, I'm logging out to the console with datetime.now. At the end of the operation, I'm logging out with datetime.now. I'm leaving it to the user to do the math in their head to figure out the time. I've got an add with timing that looks very similar. It takes two ints, it returns along, it's doing the timing things, but in this case, it's doing an addition operation. I know in the past when I've had to do this kind of stuff, these performance timings and things like this were always nasty. We'd have to go back into existing code. We'd have to dirty it up with either logging statements or things like that. Quite often, we don't want those on all the time, so we're maybe wrapping them around feature switches. If you're using something like log4net, you may be doing debug versus info versus warn type messages, but it doesn't quite fit. It's not the exact right model. So one way we could think about this is to do this with that outside-in refactoring to create a higher order abstraction. And the way I do that is I create a timer function that takes as its payload a function that has a dynamic output. So one of those new constructs in C# of dynamic, it's not specifically a functional programming construct, which is why I didn't call it out earlier, but it allows us to do some really neat things here where I don't know what the workload's going to return, and I don't really care from what I'm doing right here. So I create this timer function. And what I'm going to do is I'm going to actually generate a new function using the lambda syntax. So I return a lambda that does not take an input parameter. It is going to do the console write line. It's going to call the workload and generate the result. It's going to do the next console write line with the end of my timing. It will return the result. So this is the function, right? That whole thing gets passed back out. I create my multiply method, and this is the dirt simple version of the multiply method. In my main program now, I can declare multiplier of type func that returns a dynamic output. I call the timer with, here I pass in a lambda with the multiply function. I get back out this multiplier function that I can hang on to until I actually need to execute it. And then my last line, I call the multiplier as a function. Its result comes out. And if you watch the output out of this code, you'll see the timing calls come out and then the output call come out. So I've gotten everything I need to do. Hopefully everybody's following along with this a little bit. If not, pipe up a little bit because I'd like to make sure everybody's kind of caught in on this one. At this point, I can really start to see some higher order uses for these functional constructs. And the one that was really running through my brain last night as I was thinking through this talk was that this whole timer function, the whole performance logging or debug type logging. Loggers are good for that, doing debug versus info, but trying to figure out when to do that is hard. Trying to enable or disable that on the fly is really, really hard. But if I used the functional programming techniques, I could have a business logic method, so in this case, multiply, right? And I could set up a delegate like multiplier, and I have raw multiplier that's assigned to multiply. I could have timed multiplier that is the timer with the multiply in it. And then I could use either a database field, a config switch, an environment variable to say, if the environment variable is set, run the multiply with the timer. If it's not set, don't. Or it's a certain time of day, it's off-peak hours. I can run my performance timing during off-peak hours. During peak hours, get rid of it because it gives me a performance hit to do it. All of a sudden, I've got a lot of different options that I can bake into my code very cleanly to do performance testing, to do debug monitoring, to do a number of different things, logging of different things when I need it, all on the fly. I don't have to reload the app. It could just hit the database periodically. It could look at a Redis cache to see if, do I turn it on? Do I turn it off? And using this approach, if I do that declaration of, raw business logic call, timed business logic call, and I use a ternary expression to execute that, all of a sudden I've got an expression with that ternary that has a guaranteed output, which is my result, and I've got compiled functions that get called one on either side. So at that point, I'm running whatever operation or both operations as efficiently as I can, because I'm using compiled time things instead of runtime generated things. I've got a lot of interesting opportunities and a lot of power available to me with this approach. I know I'm getting excited and worked up over it, because as I think about all the different uses, I start wanting to really start throwing some code out there on how this could be used in real world scenarios. Hopefully you guys are starting to see this too. You can have a lot of fun with function composition, and this is where I tend to start getting kind of lost. So in this case, I've got just a main method. I create a list of numbers, 1, 2, 3, 4, 5, 6. I create a list multiplication function that will return a dynamic payload. It is defined as a lambda expression with no input, hence the empty parens, that returns the link expression aggregate that takes 2 parameters, which is 2 items in the list, and it multiplies them together to return out a new list. I then create a timed multiplication function that has a dynamic output. It is the result of calling timer on my list multiplication. I then generate my result with calling my timed multiplication, and I can print the result out. The reason the console.read line is in here is because when I was creating this, call it a monstrosity, it's a little bit of a Frankenstein creation, I had to see it go. You do really need to run this code, and I will make this code available after the talk, and I'll post it out on Twitter and LinkedIn and all that stuff. This is a little bit of a mess, right? I don't know that I would advocate for this level of abstraction, but I include this here as a way to show and highlight how deep this rabbit hole goes, right? I'm a little unwilling to jump in head first to that rabbit hole because I know it goes way far and way long. But we can do a lot of really neat things, generating all these different functions, moving things around. And really, as I was talking through some of the uses of it, we'll come back over to this one, right? The timer one and the logging really jumps to mind. And part of this came together in a different talk that I heard by some of the Azure guys a year or so back. They are really starting to advocate for logging being done in declared functions, compiled functions, with this exact technique being used for Azure workloads. And the reason being is that by using a compiled function to do your logging, you get a marked performance improvement. And I want to say either a factor of 2 or a factor of 10. And I know there's a wild difference there, but I don't remember the exact gain. That by using a compiled function to do your logging, even declaring like a function that does log info, a different function that does log debug, by using those as compiled functions and passing what you need to log into it, instead of just putting, log for net, log.debug or log.information wherever, you get a marked performance gain. That also points to a lot of why C# is introducing a lot of these techniques, is so that they can run things more efficiently in a cloud environment, right? As they're expanding the cloud and they're taking on more and more workloads, the way they can run everything side by side and well is by making sure they run as quickly as possible. As we as business logic writers, as we're moving into microservices and more cloud-based workloads, we need to take advantage of these as well so that we are using the cloud resources as efficiently as we can. Let's see. Yep, that's one of the big ones, right? We went doing that compiled function gives you some performance increases. You can see where there's the ability to pull out abstractions, to simplify what teams are doing, and to normalize what teams are doing. Yeah, as a summary, we've gone through some of what functional programming is. We've reviewed the constructs that are in C#. I've hopefully gotten really worked up and really excited and spoke really quickly about some of the ways we can use it and the things that we can do with it. And if there are questions, please start popping them up. I know I got one that I got to go back and answer here in a minute. Hopefully what you've been able to see is get a taste for what some of these functional constructs are as you encounter them, especially in ASP.NET Core, because they're using some of these constructs to create a fluent model for working with their items. Packages like Poly are absolutely using functional techniques to create their fluent syntax for doing exception handling and retry logic within code. A lot of these advances moving forward are performance increases and ways to make a developer's life easier. As the new versions of C# are coming out, they're starting to introduce even more things from a functional programming world, like records. I believe they're even starting to contemplate discriminated unions, although I'm still getting my head wrapped around those. But the record types and some of the pattern matching that go along with the record types become very powerful constructs that will kind of change the way we think about things. And I'll touch on some of the pattern matching a little bit in my Spot the Bug talk tomorrow morning. In that, as we start to go down pattern matching in C#, it's generally been a paradigm of functional programs. It's opening up new ways to do things and new ways to think about problems. Okay, so the first question that was for later was, what does this do to multi-threading capabilities? So it's an interesting question, mostly because I have generally avoided multi-threading issues by spreading my workload horizontally. A lot of the distributed computing that I've done, I've literally spread it on commodity machines horizontally and not had to worry about multi-threading. One of the biggest advantages, though, to using static functions in a multi-threading world is that you don't have to worry about state, right? That immutable concept that we talked about from early on absolutely applies here, because if I use static functions that are immutable, they are pure, and they're not mutating state, they become inherently thread safe and allow you to create multi-threaded applications a lot more simply and a lot more easily. It may even allow you to create the higher order abstractions that you would need to enable more junior devs to work in a multi-threaded code base, where that is generally something that a lot of people, their stomachs turn and they get queasy and green just thinking about it. Are there other questions that I can answer for everybody? I know I got a little bit ahead of myself and was a little bit quick, but I get really excited and worked up thinking about these things. So much so that I really kind of want to go write that timer code and put that out there in just a few minutes. Any other questions that I can answer for anybody? Again, there's my contact information. I'm really easy to get a hold of online. I'm not on Twitter, LinkedIn, or all that 24 hours a day, but if you ping me directly, I will get back to you. The talk from Jim Lyric that I went through was recorded at the time and is available at that link there. I highly recommend walking through it. I guarantee you have to watch it a minimum of twice to understand what's going on, probably about 5 or 6 times, unless you've really digested functional programming and lambda calculus. The Kathleen Dollard talk that I went to was not recorded and published, but a very similar talk that she did was, so I included that link here as well. I highly recommend it. She is a member of the Microsoft Languages team. She focuses primarily on VB.NET and C#, but she understands programming languages really, really well, and she explains them very smoothly, almost to the point where all of this seems really, really easy, even though it isn't as easy as she makes it out to seem. So unless there are any other questions, I appreciate everybody attending and listening to me talk and get really amped up about functional programming. Again, all of my contact info is there. If you want to get a hold of me online, please feel free to do so. I will tweet out a link to the slides and the code samples sometime later this afternoon or maybe first thing tomorrow morning. I hope everybody has a great day and that they enjoy Code PaLOusa. Thank you very much. You're all quite welcome. I kind of wish we could have done this in person.